Hello, hello. In this lecture, we go to chapter 8 and we talk about uh, trees, decision trees. Okay. So this chapter is about tree-based methods for regression. And essentially, it's about segmenting the predictor space into a number of simple regions. So here you can see an example of what a regression tree looks like. So this is the hitters data. It's available as part, I think, of the ISLR package. And it's a data set where we like to predict a baseball player's salary based on the number of years that he has played in the major leagues and the number of hits that he made in the previous year. And we remove observations that are missing, and we log transform salary so that the distribution is more bell-shaped, because salary is typically right skewed, and it is a standard thing to do to take the logarithm of the salary to make it more symmetric and bell-shaped. So this figure shows a regression tree fit to this data, and it involves splitting rules, where at the top we split the players into those who have played in the major leagues less than 4.5 years and more than 4.5 years. And this decision tree essentially is saying that if the player has been in the major league for less than 4.5 years, then the predicted log salary is 5.11. Otherwise, it will depend on the number of hits that he made in the previous year. And if it's less than 117.5, then the log salary is 6. And if it's greater than it, then the log salary is 6.74. And this is the mean response, okay? So this is an example of a decision tree. Tree-based methods are very simple and easy to interpret, as we can see. And a decision tree on its own is not as competitive with other methods, but we see that there are ways to combine many trees together that will lead to bagging and random forest. And each of these approaches involve producing multiple trees, which are combined to yield a single prediction. The problem is then that if you have many trees, we will lose the interpretability. But this is the data, the hitters data. So before we go to the hitters data, I just want to clarify what we mean by the log salary is 6. For example, what is that supposed to be? First of all, the scale is in thousands of dollars. So if log y is 6, then y is exp 6, and y is this is in thousands, so the salary is 403. The mean salary predicted is $403,000. So, okay, that's what we mean. So this tree stratifies or partitions the predictor region into players who have played for 4 or fewer years. This is that region. Less than 4.5 years. It's this region. I think it's the years are in integers, so when it's 4.5, it means that 4 or less. Okay, that will be region 1. And then players who have played for 5 or more years becomes region 3 and 2. But that region itself is also split into players who have less than 117 hits, which becomes this, or greater or equal than 117 hits. And then depending on where the player falls, either in one of these 3 regions, you have different mean predictions. Okay. So these 3 regions are known as terminal nodes or leaves of the tree, which refer to these 3. So these are 3 leaves, 3 terminal nodes. So how do we find the trees? Essentially, we want to find a partitioning of the space such that, for example, the residual sum of squares is minimized, and that partitioning has to be along the dimensions horizontal or vertical, and we can split the space. We can have these lines vertical or horizontal, and within each region too, but we can't have partitioning of the feature space as we see here. Okay, and this partitioning corresponds to this tree. X1 less than T1 is here, and then depending on what X2 is, we have these 2 regions. X1 greater than T1, it's this, and if it's less than T3, we are region 3. If it's greater than it, then we have the 2 regions split, R4 and R5. And then once we have these regions, then we predict the response for a given test observation using the mean of the training observations in the region. So if somebody comes up with a new player that has more than 4 years experience and less than 117 hits, then we fall into this region, and the prediction will be the mean response of all the points that are in this region. Now, the question is that when we do the splitting, how far do we want to go? Because the way it's done is that we use recursive binary splitting to grow a large tree. So we split the space along dimensions and at thresholds to minimize the training error. And obviously, we can continue this as far as we want, even to the extreme case where the number of observations per region are just one, and then you have a perfect fit. The problem is then that this tree might be overgrown. So one way to approach that is to apply cost complexity pruning, where we start with a large tree and then we get rid of some of the nodes so that the cross-validation error becomes as small as possible. Okay. So here's an example. That this is an overgrown tree. It's a tree that is grown to the extent where in each region we have at most 4 or 5 observations. And then we can have look at the cross-validation error as the tree size. So we have the mean squared error here, and then we have the test MSC, we have the cross-validation and the training. Obviously, as the tree size increases, the training error decreases because the tree becomes more complex. And as the tree becomes more complex, it will fit the data better, but doesn't necessarily lead to a better testing error. And it seems that the tree size that leads to the smallest cross-validation error is 3. And that's a right balance between complexity and training error. Sorry, testing error. Okay. So this is how you can. This is essentially trees for regression. We skip trees for classification because that's doesn't belong to this course. It's another course. Trees for classification will be discussed in the machine learning course that is offered in the fall. Okay, so bagging, and there is random forest, and boosting, they use trees as a building block to construct more powerful predictions. So what is bagging? We create B bootstrapped samples from the data. We fit a tree to each of these bootstrap samples. We average the trees and we get the bagged tree. So these trees are grown deep and are not pruned. These trees, each of them, are very well fit to that bootstrap data. And the problem is that when a tree is fitting the data very well, it has a high variance. It has a small bias because it's very flexible, but it has a high variance. And because of that high variance, we create these bootstrap trees to average them out, because averaging is known to reduce variability. So bagging was introduced to remove the variance, to reduce the variance. Okay. And bagging stands for bootstrap aggregation. So by averaging a set of observations or the responses, we are reducing the variance. Now the problem is that these bootstrap samples have a significant overlap. And because they have a significant overlap, these trees, their predictions will have a significant amount of correlation. So one idea was introduced to reduce the correlation between the trees to create random forests. But let's wait for that before. I just want to go over a few points here. So, because each bootstrap tree uses only, roughly speaking, 2/3 of the data, that's because of the bootstrapping. So these bootstrapping is resampling the data with replacement. And because it's with replacement, some data points are repeated. Okay, and because it's repeated, some data points are not used, and one can show that on average each bagged tree uses only roughly speaking 2/3 of the observations. So 1/3 of the for each bagged tree, 1/3 of the observations are not used to train that tree, and therefore this creates a natural way to estimate the test error, which is in this case known out of bag test error. The remaining 1/3 of the observations not used to fit the tree can be used to estimate the test error. We can predict the response for that observations using the trees that. So for each observation, there is roughly b over 3 trees that are not using that observation. So we can use the prediction of those trees and then compare it with the observation we have to estimate the test error. So the out-of-bag test error is, roughly speaking, a good estimate of the test error. That's something we like. So bagging improves prediction accuracy but loses interpretability. Why does it lose interpretability? Because now we are dealing with many trees. One tree is easy to look at, to visualize, and because it's easy to visualize, it's interpretable. But when you have many trees, then we lose the interpretability. So what are we going to do? How can we get some interpretability? In other words, how can we measure the importance of each predictor? That's very difficult for trees, and the importance we get is hard to be used, but there are ways. And how can we do it? So for each predictor, we can see that how much does the residual sum of square increase, the RSS increase, if we remove all the splits over that predictor for each of the trees. And then we average over the B trees, and that gives us a sense of how important the different variables are. Here you see we have a variable importance, which is whatever a num. I wouldn't really put too much into the absolute value of these numbers. Rather, I would just use them as a measure of relative importance. Okay, random forest. So what was the problem with bagging? The major problem was that the trees were highly correlated because they were trained on bootstrap data sets, and the bag trees were grown to fit the bootstrap data sets. And because the bootstrap data sets have a significant overlap with each other, so will the grown trees have a significant correlation with each other. The random forest is a way to improve bagging by decorrelating the trees, and the way it's done is that when we grow a tree, for each possible new split, instead of allowing all the predictors to be in the pool to be selected, we say randomly select a subset of the predictors, and among those choose the best split. So we inject some noise, some randomness, and limit the trees, which will reduce the fitness of each tree to the data, and it will also include some variability. So each tree from the different tree will look very different, because first of all, we don't allow them to look at all the predictors. We only allow it to randomly pick a small subset, and moreover, that subset is random, so therefore the trees will be less correlated, and the number we typically use is square root of p. Okay, yeah, we skip this. So these are the errors. As we can see, as we increase the number of trees, nothing really changes. In the beginning, it does, but so the number of trees, excuse me, the number of trees do not play a role of complexity. So typically 100 trees is sufficient, 200 trees is sufficient, and after that there won't be a big change in the error rate. Here we see the test error of bagging, and here we see test error of random forest. And we see random forest has a smaller test error. Okay, so this concludes the first part of the trees. The next part will involve coding with simulated data and real data. And then in the next part, we will talk about how to implement trees in R. Thank you.